So you can rewatch then the recording of this lab if you need to, but you don't have to then worry about watching that video lecture 3 for this week. Okay, so in this lab, I gotta get back to my Word document. For parts 2 and 3, or what you're going to be doing this week to complete it, you should have completed part 1 last week. We're studying what's called a Windkessel model, which is an electrical circuit equivalent of blood flow through our vessels. And there's several different Windkessel models of how you can model this. A very simple one is this called 4-element Windkessel model here, where I have 2 resistors, an inductor, and a capacitor. And I can think about the voltage for each of these as equivalent to blood pressure, and the current, electrical flow current, equivalent to blood flow. Okay. And I need resistive elements because my blood vessels do provide some resistance to blood flow, particularly if they're narrowed due to a plaque or something like that, or if they're just a very small vessel. I also have a capacitive element because my blood vessels can store blood like capacitors store charge. Particularly, our veins can expand to kind of pool blood and keep it as a reservoir. And I have an inductive element from this inductor here, because your vessels have an elastic capability that keeps blood flowing through them so they can kind of maintain this pressure, just like an inductor wants to keep electrical current flowing through it. So we can use this model to again mimic blood flow, where blood pressure equals voltage and blood flow is current from it. You're going to need to be able to calculate the transfer function for this circuit for part 2. For part 3, I tell you all the transfer functions in terms of our variables R1, R2, C1, and L1, my inductor. So this was actually, again, in the lecture that I was trying to talk about. R1 and R2, again, model kind of our resistance to blood flow. And that resistance would increase if our area decreases, of the cross-sectional area of a blood vessel decreases due to a plaque, or even just going through capillaries, or a higher resistance than like a big wide artery. Our L represents inertia of blood flow, and our C represents capacitance, or the ability to store blood or pool blood in charge. Normally, this Windkessel model really refers to the effect of your blood vessels to allow expansion when pressure increases. Particularly, your arteries will expand to absorb a pressure wave, and then they can release it slowly with kind of this elastic recoil to keep blood pushing through in a pretty steady manner through your body. So it's not like that you don't have any blood flowing when your heart isn't contracting. You do still have some blood flow because your blood vessels are able to maintain that flow over time. Unfortunately, this ability of your blood vessels to maintain flow from expanding and then contracting to kind of maintain a constant pressure, or near constant pressure, it does vary some, decreases with age. So the older you get, your arteries can't expand as well. They also can't contract as well from it. And you don't have as a good of ability to modulate blood pressure like that. So keep that in mind. Y'all have it the best you have probably right now in your early 20s. Since we can, while we're coming up with a transfer function for this equation, as a reminder, I get to do this based on impedance of these circuit elements. So what is my impedance of a capacitor of C1? You can type in the chat, or you can unmute a mic. How do I write impedance in S domain for a capacitor? 1 over CS, good. What's the impedance of an inductor? As a reminder. My inductor L1, good, LS. So I can use those to then come up with my transfer function. My transfer function here is the voltage out over my capacitor and resistor. It's kind of the voltage in my further blood vessels compared to implied voltage in, like the blood pressure coming from my heart. And I want that relationship between pressure in my vessels downstream compared to pressure in my heart. So to calculate V out, if it's a voltage drop across this capacitor, it's also the voltage drop across this resistor, because they're related in parallel, right? This resistor is in parallel with C1. So how do I combine them in parallel? I have to do R2 times 1 over CS over, add them on bottom, R2 plus 1 over CS. And then I've got to make that pretty, right? I don't like fractions over fractions. So I multiply by CS over CS, and I get R2 over R2 CS plus 1. That's the equivalent impedance of these two elements. To do V out over VN, I really want that equivalent impedance, what I'm calling Z equivalent 1, over my total impedance for this circuit. How would I get my total impedance for this circuit? Now that I already know Z equivalent 1, what do I have to do to combine it to get my total impedance from like here to here all the way across VN? How is this parallel combination related to, or how is it connected to my inductor and resistor? It's in series. Good, Christian. Addison, yeah, so if I have Z equivalent 1, I can add it to the impedance of R1, which the impedance of resistor is just a resistor. I do need to differentiate R1 and R2 because I have two of them here. I don't care if you differentiate C's because there's only one C and one L here. And then the impedance of my inductor, which is SL. Right. Keep in mind, Z equivalent 1 is this whole mess, so you're also going to get fractions over fractions, which you need to multiply by that denominator then on top and bottom to clean that up. You should end up, as a hint, for your total transfer function as a second order system, which means on your denominator, you should have S squared times something plus something times S plus something times not S's, or S to the zeros. Right? And those numbers, well, those variables, because I want you to leave them as variables in terms of R1, R2, L, and C1, are what we're going to end up typing into LabVIEW to program as this transfer function. Okay, so you need to be able to combine all of your S squared terms, all of your S to the 1 terms on the denominator, all your S to the 0 terms, and whatever you have on the numerator, although as a hint, your numerator should be pretty simple. Your denominator is pretty complex though. But it is a second order system. Makes this, you will get an S to the second. And we've studied second order systems, right? We could have different responses for a second order system. We can have undamped responses that oscillate but then die out in time. We can have, underdamped responses that oscillate and die out in time. Undamped would just oscillate forever. You probably don't want that. I do want it to approach a final like blood pressure value if I give it an input of that, right? That's what I'm really talking about in terms of this voltage is like blood pressure. I also had overdamped models or critically damped models. And while they didn't have any overshoot, they rose more slowly, particularly overdamped ones. You would have an overdamped system if you have a really high resistance value, that's a hint, which means it takes a long time for your blood pressure to adjust, which probably isn't what you want. Okay, so you're okay even most of the time if your blood pressure going a little over its final value, as long as it responds pretty quickly to those changes. So an underdamped system might be okay. An overdamped system where you have an input of blood pressure and it takes a long time to rise, or for that blood pressure to kind of think about getting towards the rest of your blood vessels and the rest of the body, wouldn't be a good model. But that is what happens as you age. You get a higher resistance for your blood vessels and your blood vessels become less responsive in time. So keep that in mind when you're looking at your responses to that system. So we're going to be graphing that equation, or 4-element Windkessel model, which you need to come up with the coefficients in terms of variables. Well, I'll show you how to program that in LabVIEW in terms of those variables, so we don't have to calculate them by hand like we had before. We're going to have a more complex Windkessel model, which is this whole scary circuit here. I promise it's not really that bad though. I don't make you come up with the equation for this on your own. I give it to you. So for those of you who are freaking out, can relax, but we do need to understand what this circuit model is doing. So this is actually modeling part by part, kind of the blood flow all the way from my left side of the heart, from what comes in through my atria. Remember, the atria are the top chamber of your heart, or kind of your storage chamber. So pressure, again, I can think of as like voltage at a point on this circuit. So this PR value here is the pressure in my left atria. I also have a capacitance value for that atria, CR, because our atria are basically a storage chamber for blood. They can contract a little, but they aren't really a great contractor. They basically just kind of store blood. But a capacitor stores charge, and we're saying charge is kind of like our blood. Movement of charge is blood flow. Total amount of it would be like our pressure in a certain area. So I have a capacitor value for that atria that can model that electrically pretty well. From my atria to go into my ventricles, I have to pass through the mitral valve in the left side of my heart. That valve is intending blood to only flow in one direction, right? You don't want blood to flow in reverse going from your ventricles back into your atria. That backflow, if you have that, can be a problem called atrial regurgitation or mitral valve regurgitation. So that valve, that mitral valve, is represented by a diode. Remember, we've seen diodes before in sensing and measurement. They're an arrow kind of with a line, and that arrow is indicating the direction they allow flow. Why would I want a diode to model my mitral valve? Why is a diode a good choice for an electrical circuit element to model that mitral valve? Yeah, diodes only allow current in one direction, or at least they only allow current until you get really high of a voltage in reverse. You said breakdown of a diode or a reverse connection, reverse bias. The same thing happens with a mitral valve. If you had really high pressure in the ventricles, it might cause backflow. But in general, they only allow flow in one direction. So it's a pretty good model for it electrically. That valve also has some resistance because it's a narrowed path for blood to flow through. So I modeled that mitral valve with a resistor as well, RM. And I can talk about the flow through that valve by modeling the current through these elements right there in series. That flow through my mitral valve is what I'm calling FR here as a function of time. Okay. I then, from my mitral valve, enter my ventricles, and again, could measure pressure in my ventricles, like measuring voltage at this point on my circuit. So pressure isn't really an element, it's just measure voltage right there. My ventricles, though, are a storage chamber as well, so they're a capacitor, but they're a capacitor with this arrow through it, which really means a time-varying capacitance. So your ventricles have the ability to expand more and more, even more so than your atria do. And as they expand with time, they can store more and more blood. So they're a time-varying capacitance, a special value for that. So C is not constant, it varies with time. Once I get through my ventricles, though, my ventricles contract and send my blood out through my aortic valve. And there's another valve there, so it gets a diode and a resistor to model the flow going through it. And I can call the pressure in my aorta once it's gone through that valve, PA here. That would be like the voltage at this point in my circuit. The flow through this wire in my circuit would be flow through the aorta as a function of time. Again, like electrical current. Once I get through my aortic valve and my aorta, the flow through that, I then go to all the rest of the blood vessels in the body. And this model is still a simplified one. I know it doesn't look simple, but it kind of lumps all the rest of the blood vessels together. So this RC here is a characteristic resistance of my arteries. And they have some resistance that actually increases with age, which is bad. They have an inductance of all of your systemic vessels because, again, there's some inertial forces that keeps blood flowing, which is good. In general, keeps it from pooling in places like your feet until you get older, and that effect goes away as well, which also isn't good. They also have some storage capability, CS, from capacitance. Again, particularly your veins can store blood if needed. And I could measure the pressure in my systemic vessels as this PS. The voltage at this point in my circuit would be equivalent to the pressure in my systemic vessels. I also have a resistance going through all those vessels, RS, and then it feeds back into what I'm assuming here is the atrium, the left side of my heart. This is really lumping in also the whole right side of my heart and my lungs. I'm not showing that in this model. You could divide them into their own little parts as well, but it's kind of lumping in resistance, inductance, capacitance, and this for all of that side of the heart as well. Your right side of your heart isn't, it doesn't expand as much like your left ventricles do either. So it's not as effective from it, but you could make this model more accurate if you had separated the right atria, the right ventricles, their valves accordingly into elements as well. So this is our more complex Windkessel model. We just need to kind of understand what those elements mean. So if we changed one, what would it mean? And luckily I give you what the actual transfer functions for these are under two different cases. So during ejection, when blood is being ejected out of the heart, that's because my ventricles are contracting, right? So what I get is my transfer function here is I really want to look at my output is flow through my aortic valve, right? Because that's a blood coming out. Well, it flows based on what pressure is going through the aortic valve. So my input is the pressure, my output here is the flow. So that transfer function of output over input gets me this equation here. It is a third order of the bottom equation. So I get coefficients for s to the third power, s to the second, s to the 1, and s to the 0. On the numerator, I have s to the second and s to the 1, but no s to the 0. Do note that. And again, I don't make you come up with these because that's a more complex equation to look at that circuit. But I am told what each of these coefficients are based on L, my inductance of like my systemic vessels, resistance of those vessels, capacitance at each part, everything like that. So you don't need to know what these are. You just need to plug them as a variable and use the numbers given here. Okay. Another transfer function that I could look at from that circuit is during filling. So during filling of my ventricles, the output I want is what pressure gets into my ventricles, right? Because they're going to keep on expanding as they go. And what's coming into my ventricles is the flow through my mitral valve. That was my FR variable in that circuit. So I get this equation for the transfer function. Output, pressure in ventricles, input being flow in the mitral valve. Again, coefficients are given to me here based on those circuit element values. I just need to plug and chug them and use them. So we'll look at these and see what they make of sense from it. One thing to note, so these equations came from a research model from your lab book, if you did look at that. I'm trying to explain it so you don't have to look super at the lab book, but you can use it for reference if you'd like. Your book chose to, once they defined each of these transfer functions for during ejection and during filling, they integrated them. So they really integrating, remember we said is the same as dividing by S in S domain. If you differentiate, you multiply by S. So if you divide by S, you integrate. So they really take each of these transfer functions and they multiply them by a big fat 1 over S. Why did they integrate? It's a little weird. You could actually look at these without integrating if you wanted to. But for one thing, it makes a little more sense in our injection model to integrate because I'm talking about flow as my output versus pressure in the aorta, right? Flow through the aorta versus pressure in it. And flow rate, if I'm talking about blood flow or water flow or whatever it is, normally has units of volume per second, right? Like meters cubed per second or milliliters per second. When you integrate that, you now are total volume. So it's easier to think of instead of flow, like at time, would I have higher flow or lower flow? Just talking about total volume of blood that has kind of passed through my aorta over time. That's an easier relationship to think about. You could think about the same thing if you're integrating during filling, because I have flow here. But really what it's doing is integrating more pressure, which helps smooth out changes in pressure waves due to any error you had in your model of like your pressure changing very quickly. Because your instant pressure really doesn't change that quickly in the heart. It does change over time. So even we're going to model this with a step input. It does a little better if it's integrated. I don't expect you to have to explain why they did an integration from it, but I would like you, as we'll see in LabVIEW, to actually put put them both multiplied by an integrator function or multiplied by 1 over s. Okay, so what do we get when we graph these? During ejection, you should get, I'm even telling you what your time response graph should look like. We're going to look at other graphs too, though, so this isn't just your final only answer. You need to do the lab yourself to get the rest of those graphs. During ejection, I'm again talking about flow in my aorta over pressure in the aorta, and I get this step response. Again, to a unit step input, I get a response that ends up looking like this. Again, because I integrated flow, this is really talking about my total blood volume over time, and it makes sense that that volume would rise quickly initially and then kind of flatten out as I reach my total amount that I could have had from my ventricles anyway, right? It's not going to just keep going up for forever. But this transfer function also, I note my coefficients here are all positive. That's because I have a positive relationship between the more pressure in my aorta, the more flow I'm going to get out of it. So this transfer function should be positive for me. That's the most you need to explain for it. During filling, this was my transfer function. Again, filling is dealing with pressure in the ventricle as the output, to that the input being flow through the mitral valve. And I get a negative on this numerator. That's because there's an inverse relationship. If you think about your ventricles, the only way they get more flow into them is that they actually expand. Again, they're time-varying capacitance. And as they expand, their pressure drops. And that's what causes more flow in through the ventricles. So if I had decreased pressure, I actually get more flow, versus if I had increased pressure in my ventricles, I wouldn't get as much flow in, right? It's really only a pressure difference between the atria and the ventricles that allow blood to flow through into the ventricles. So I see when I graph this step response in time that I'm actually getting a decrease in time, or think about it, decreased pressure per compared to flow from it. As flow increases, my pressure actually had to decrease from that. That's the only way I got increased flow through it. So there's an inverse relationship during filling that I don't have during ejection. Okay, we are going to be using LabVIEW to model these, and I think the rest of this I'll just talk about actually in LabVIEW of how to do that. So if you want to follow along with me in LabVIEW, now you are welcome to do so. So we're going to be doing basically the same program for part 2 when you're doing this 4-element model, that you need to come up with the transfer function yourself, again, based on its coefficients of s. And then part 3, where you're doing the more complex Windkessel model for both ejection and filling, where I've given you the transfer functions for them. But your program's basically going to look the same. You're just going to change the coefficients for your transfer function for each one. For lab 2 for its cases, and then, for part 2, and then for part 3 when you do filling, and part 2 when you do ejection, or vice versa. I said them in the wrong order here. So our program will literally look the same. What will that program look like? Let me open blank block diagram in LabVIEW. So one thing we're going to start is we're going to program this with a math script node. Again, if you don't have that already, when you right click on your block diagram, you want mathematics, script and formula, and then math script. And kind of like our other loops, you kind of got to click and drag to give yourself space to do that. Why we are going to use math script, it basically allows you to code like you are in MATLAB, and that's going to allow us to type in variables and use variables, and you get to program them in instead of, as you saw like in lab 1, when you had to make a transfer function in LabVIEW and I asked you to change some of the variables, like you were changing the spring constant or mass in your mechanical systems, you had to keep up with what that number was and hard code in the number in LabVIEW. And that was really annoying when you just changed a variable and it would change many things in your equation. Here, I can now program variables and make the computer program deal with all of that for me. So I don't have to keep up with what number actually changed from that. So get to use variables when we get to use MATLAB. So you want to define your variables. You have R1 equals something. I'm not going to be typing the correct values here. You need to do them on your own. I'm just giving examples. I'm typing in random numbers, so do note that. And please stop me as we go along if there are questions about this. Otherwise, it's really weird talking to a screen that no one talks back. So I have my inductor. Again, these are not the right values. You need to use your own. Whatever. Okay. In MATLAB, instead of again having to use LabVIEW to program this, I can make vectors for the numerator and denominator. I think in your lab handout I call them num and denominator, but I'll call them that here. To make a vector, if you remember MATLAB, you have to open a bracket and then you can type your variables, again, if you define them here. So I can type it based on R1, R2, if that's what I want. My denominator, I can make based on, I don't know, L1, again, this is not correct, and C, something like that. Semicolons technically suppress the output, but I don't actually see the output here in MATLAB when I'm in LabVIEW with MATLAB embedded, just FYI. So this makes a vector of my numerator and my denominator. I want to point out a difference that I kind of went through in the, again, the lecture for this that I was trying to talk about, between how LabVIEW makes a transfer function based on coefficients and how MATLAB does. So if you want to use LabVIEW to make your transfer function, you can go to Control and Simulation and say Control Design, Model Construction, and say CD construct transfer function. And I get inputs for the numerator and the denominator. I'm going to leave this with a label. So I want to be able to wire in a numerator and a denominator. To get things out of MathScript and into the rest of LabVIEW, I have to make an actual output from this MathScript node. So I click on kind of the blue node and I say add output, and see now you get any of the variables that you just defined. So now I can make my numerator an output and I can wire him where it said numerator. I can do the same thing and say add output denominator and wire him to where he says denominator. If I then display this, you don't have to follow along for this part. If you want, I'll actually be showing a simpler way. I just want to point out the difference. Under Control Design Simulation and Model Construction, I want to be able to display this transfer function. So I'm going to use the command CD draw transfer function equation. Seems kind of silly, but otherwise you don't see it written as a fraction with the variables of S. All I see is his coefficients. Give this guy a label too. And what he wants is my transfer function model, which is what comes out of here. And his output is my equation. If I right click again on outputs and say create, I can create an indicator to display that. Okay. That's using LabVIEW to make my transfer function. In MATLAB, I can actually just use the command TF, open parentheses, and give it my variable for my numerator and my denominator. Just close parentheses and save that to something. So I can call this my plant or whatever you want to call it. This is kind of equivalent to using this transfer function model in LabVIEW. It just acts in reverse. So I'm going to show you what happens here. I'm going to wire my plant out. That was under Control Design, Model Construction, CD, draw my transfer function equation. And now I need an output for my plant variable. Since I use that, if I wire that in, give this a label, visible items label. And I make him have an indicator for that equation. He's equation 2. I'm going to run this to see what the difference is. What do you notice is the difference between these two equations in terms of their coefficients? Yeah, they're flipped. So in equation 1, 2 was my coefficient for s to the 1, and 5 was my coefficient for s to the 0 on my numerator. Equation 2, 5 is the coefficient for s to the 1, 2 is the coefficient for s to the 0. There's an annoyingly and inherently a different way than that LabVIEW makes a transfer function versus MATLAB does. Okay, and I tried to explain that in those slides, so I'll go back to that. That in LabVIEW, if you're making a transfer function with numerator and denominator, and you use that CD construct transfer function, like we kind of have been using, it wants the order of those vectors to be increasing power of S coefficients. So you start with the S to the 0 coefficient, then the S to the 1 to the S to the 2. So if you want to do that, you can use the LabVIEW icon construct transfer function. If you use MATLAB's command TF for transfer function, and you feed it the numerator as a vector, the denominator as a vector, it wants those vectors to be in decreasing power of S. So start with your highest power of S, like S to the 1, then go to S to the 0. Okay, they're just flipped. I don't care which one you use. You don't need to use both. You can just use one, but you got to know the difference between them. And it confuses people because we are sometimes used to LabVIEW doing that, and we plug them in a certain order when you were hard typing it, and now we're going to do something different. Okay, so that's making my transfer function. The other thing we are going to graph from it is our step response, like we've done before. So control and simulation, control design, time response, CD step response. So we can look at what does our equation do. I'm going to assume that I used my MATLAB one. Again, you could use either, just make sure your coefficients are correct. These are not the right values. And the only thing that's going to change from your part 2 of your lab to part 3 with ejection and part 3 with filling is what coefficients you type in there. I'm going to wire that state space model to here. That's my step response, and I want that as a graph. So I click on the output and say create indicator for it. And anytime you have an output of a LabVIEW icon that you just want to see on your front panel, right click on that output and say create indicator. My step response, the other thing I want to look at, besides your equation, you do need to display your equation to make sure it's written the way you thought it should be, is your Bode response, your frequency response. That's control and simulation, control design. And that's under frequency response. And you want to say CD Bode. We learned about our Bode graphs, that they graph how our system would respond in frequency. So now I can wire state space model here, this same point. Oh, why did you make me unhappy? There we go. The output of that, I get Bode magnitude and Bode phase. It will do both those graphs for me. Again, the whole nice thing about computer programs is they can do a lot of the work for me. So to each output, I right click and say create indicator. That made my Bode magnitude graph. The nice point of doing this from saying create indicator instead of like going to your front panel and making a graph is it also names them appropriately for you, which is nice. Create indicator. Okay. So we have those. Let me double check what. Oh, and it wanted all those, sorry, I missed a step in here. It wanted all of them put in a feedback loop from that transfer function. So to put them in a feedback loop, we had done that when we were in simulation before, and we actually wired a loop backwards and added them. We can do the same in control design through an icon that puts a feedback loop. So I go to control design and it's model interconnection, and I say CD feedback. When I do that, I'm actually going to delete this little line here to feed it to it. What I feed into this is my first model. That's like my forward gain. If you wire something into model 2, that would be like your loop gain. In this case, I don't want any loop gain. I'm just going to assume it's 1, or it assumes a general negative feedback loop. And then I can wire the output to all of these. So I'm going to put them all through a feedback loop. I think your lab handout instructions told you to put them through a feedback loop before you look at their Bode response. But I actually probably didn't want that before I did my transfer function. I now have a whole bunch of wires going everywhere. If you get that with yours, click the broom, and it makes things in a nice order. Okay. The only thing I didn't want is I wanted my transfer function equation not after it went through that feedback loop, because as we'll see, that will actually change your equation. I wanted it to just be what I had from here. So I'm going to remove this wire, change his input, delete that wire, to be just from my plant itself. So not through the feedback, but I do have the feedback for my step response, my Bode graph, everything like that. Now click on Broom, see what I get. So just my plant went to my transfer function equation to display it. That's how I can check that my coefficients were correct and in the right order based on what power of S I thought. And then my feedback loop I went through before I looked at my frequency response with my Bode graphs and my time response and my step response. Again, you would not need this to display the other transfer function model if you use the MATLAB command. If you did use this command, then you'd be wiring out of there to the other things. Either way, though, that you want to do it, that's fine. When you run these, now let's look at, I have my step response graph. Again, these aren't the right numbers. I get a magnitude, Bode magnitude graph versus frequency. Notice my frequency is in powers of 10 increments or in decades. My magnitude is in decibels. My phase graph I also get as well. So it graphs all of that nice, good stuff for me. And that's basically all you need. When you have part 3 of lab, and I said that each of these transfer functions, how your lab book had done them, was put them in series with an integrator. So it integrated both of them. You're told to make another transfer function that basically integrates, just multiplies by 1 over S, save that as integrator, and put them in series. So how do I do that? Back to my block diagram. After I made my plant, I could make a function I'm calling the variable integrator, and it equals transfer function, where my numerator is just going to be 1, right? And my denominator, I want to be just S to the 1, which is really, if I'm using MATLAB's rules, highest power of S to lowest power of S, that is 1, 0 as a vector. And then I close my parentheses. I want to multiply that integrator function by my actual plant. So I say series is the command in MATLAB. You could do, like we did, a feedback icon. You could wire them in series if you wanted to use the model interconnection in LabVIEW tool, so control design model interconnection. There is CD series. If you prefer to just wire each of them out and then into that, that's fine. If you want to just use the MATLAB command, though, you give them each of the variables. So I called this one plant, I called this one integrator, and now I put them in series, and I need to save that to some variable. Oh, that's annoying that I can't see my whole thing. I have to save that to something that I'm going to call like my whole system, just needs to be some other variable. And now I don't want to be graphing my plant, I want to be graphing my system. You can either click on your output and change its name. If I go to tools, where is my view tools palette? And click on my A, I can change the name as long as I change it to exactly what I called it here, system. Or you could have wired the output itself by saying add output, and if you hadn't wired system, you could use it. But for part 3, when you're doing those Windkessel models from that complex circuit, you do need to put them in series with an integrator before you graph them. So I need my integrator function here that was just equivalent to 1 over S. Okay, that's it for it. So you should have 3 extra screenshots of your front panel, one for part 2 of lab where you're doing that 4-element Windkessel model, and you needed to come up with the transfer function yourself and its coefficients. That's why it's helpful to use variables here, and then you can use those variable names in your numerator and denominator. In part 3, you are given the transfer functions. You have 2 different ones, though, one for filling and ejection. So you've got to run this once for ejection and then once for filling. All you're doing is changing these coefficients, and you don't really need the variables here. You can just type in, if you want to call your variables A3, A2, A1, type in the numbers that you're given for those. Okay. That is the end of talking about my lab. Sorry that was long. I was trying to do it in the lecture beforehand, but apparently that recording didn't work well. So Questions or concerns now, because that was a lot. And again, this is recorded that you can go back and look at it if you would like. Can y'all still hear me? I'm nervous now that no one says anything. Yeah, I know it's hard when you're just trying to do it. Again, I'll stick around if you want to be working on it and have questions. If you have questions on anything else, if you have questions on homework or lectures or anything, I'm happy to do that too. Sure, feel free to lurk, Sonia.